So this, we're going to keep working the same survey. So actually, this is just onshore from Matagorda Island. I mean, it's not that far. It's onshore Texas, a little bit north and east. Now, this survey is public domain, but it's been, I'm going to call it sanitized. So it's not in its true orientation because it was released. They put false orientation, false coordinates on it. But this is, we call it the Stratton data set. And it's a very good data set. So one thing I wanted to do here, you know, we did talk quite a bit about data management today. And as we said, it's really a critical issue because there are 10,000 things that can happen in the data management side of things. So let me see, I thought I turned on, well, explore. Ah, there it was hiding on my other screen. So this, again, every workstation has its buttons in different places. So don't get caught up on the specific buttons here. The main thing I want you guys to just get used to is the principles. So this happens to be one station, and this shows you different elements of what you load in here. So, you know, in a comprehensive, integrated, multidisciplinary study, you will load everything here. So even evolve, you know, we're giving you kind of a partial data set. But for example, you know, if you were really operating these wells, and so, you know, we have whatever, about 20 wells in this particular project, if you were actually drilling these wells and operating them, you would have very extensive borehole notes and remarks. You would be tracking your completions in detail. Basically, you know, what kind of completion, which formation, whether you're doing gravel pack, mesh size, when the completion began, et cetera, et cetera. So, you know, that's just one example of that. Composite logs, this is something usually put together. Almost any well or field, when you're working in an oil company, you're going to have core data. So we're not specifically going to give you core data in Evolve. It's hard to come by, but that's key. Cumulative production, you know, ultimately, this is where the engineer in an oil company will gather all the production data and then we'll load it. And again, you have to get it in here, you have to QC it and so on. Deviation surveys, most of you are working with that. The digital logs, of course, you know, we talked about that, and it's important to be able to review those and QC. And, you know, like we said, many different kinds of checks you can do on those. So this is just one example. So here's my SP log in this particular well. This is an old log called the short normal, SN, etc. But the key here is look at all these data types, drilling events, and then of course things like formation tops. These are things you will be working with. But just remember, a multidisciplinary exercise contains any and all of these different types of data in here. And so, for example, this is when you guys have done your biostratigraphy work in here, and you've related the wells and the seismic, then you'll have your own tops in here, and you'll be putting those in. Oh, it's a bit slow here. So you, in your case, you will not have the, and this is, by the way, this is another case right here where these reservoirs are Frio formation, which is Oligocene, and some of you will have Oligocene targets, but in this particular case, they've come up with their own naming system. They don't want to write all those long bug names. So in this particular field, they've called them sands B, C, D, E, 49, 50, so etc. But again, the main thing here is to realize all these data types and all the information that you really compile and again, constantly do quality control on over the course of a project. So very comprehensive. Okay, so, you know, as we said, we've got about 20 wells in here. Let's go back in here. So actually 21 wells. And of course, this is the area of the 3D survey in here. And one thing I wanted to mention is we showed last time how you can post all sorts of information from your wells. So any of this information we were just looking at, you can post on the well. And so one thing I'm going to do now is let's go to, I want to look at which wells have a particular formation top. And let's just say I'm going to look at, pick one, D11 here. Okay, so there's the wells that have the D11 top and whatever, F21. We'll give it a different color, etc. And whatever, let's pick the deepest one, give it another color. So again, knowing what's what, knowing which wells have which kind of information, we'll show the legend here, is critical. Okay, so far, you know, we've talked about, why do we say integration? We say integration because at the bottom line, we work in two domains. Seismic is recorded in two-way time, as we well know, and that is the only absolute measurement in the seismic domain. So when someone gives you a depth section, and one of the teams has that, that is an interpretation. And then when you work with wells, the only true measurement there is depth. And so the whole point is you are working constantly in time and depth, and you have to go back and forth. Anyway, so you may recall last week we did some picking of horizons in here. That was done in time. And so these are time data sets. So what I wanted to look at next here today is how you can work with formation tops and make quick maps of those. So let's say that I want to, let's look at the D11 top. So I want to come in here and I want to see more or less what the shape is in depth, because right now I've only got time. I'm not sure exactly how things are structured. So basically what you do is you come in here and you're going to create a grid. And whatever, the red one, we'll call it, we said D11. We're going to do a grid on D11. And it's important to constrain that grid, because if you don't constrain the grid, it's going to go off in other directions. And when I say constrain, I'm actually talking about geographically. So you'll take a polygon, and that's the red outline in here. So I want my grid to be within that polygon, so it doesn't go crazy projecting things outside my area of interest. So we've made a grid. It looks like there's no grid, but there actually is. And I'm going to just, there's my grid. So this is our first depth map, and let's see, again, I'm used to working on two screens, so it's a little cramped trying to work on only one. Let me get my zoom images off that screen and bring this in a little bit. And so this, you can see that essentially we just began with a handful of tops, and we had picked the option, by the way, you may have seen, if you look closely here, you can make your grid. Of course, if you have time data, you can make a time grid, but you can decide whether you're making your map in TVD, seismic, true vertical depth seismic, or subsea. I elected to do this map in subsea. So this is a subsea depth map. So 4,920 feet below sea level to about 5,000 feet below sea level. So that's the depth we're looking at. Now, one of the keys of gridding is that you're interpolating very sparse data, right? If we go back to our original points, that's very sparse compared to seismic data. And so our mathematician friends have developed all sorts of algorithms to do gridding. And so we did one here, which is called flex gridding. And let's try another one here, which is someone got a PhD writing a different algorithm. And we're just going to, in this case, overwrite it. And in this case, it's a different color bar, but that will have a different shape. Let's do, actually, let's go ahead and try another one here. Inverse distance. So this time I'm going to actually give it a name. So it's going to make me a new map. So what you're going to find is that most workstations have 10 or 20, some have even more algorithms. and they all create different grids. So you can see some of the differences here in depth. Actually, let's do one more. So we're going to next apply another one. So we've got now our one called distance, inverse distance to a power, and now whatever. Let's go see what else we have on the menu here, whatever. Let's go natural neighbor, which is a different technique, and I'm going to give this one a new name. That apply. And there we go. So you can see that one actually is very different in the technique that it did the gridding. Some of them will interpolate longer distances, some of them will interpolate shorter distances. But I think you can see here now that this is quite a different looking map. So for example, in this one here, the natural neighbor, if you were to take this grid at face value, it would suggest in this western corner, we've got like a northeast southwest trend. If I go to this other technique, inverse distance to a power, suggests an east-west trend. So again, this shows you that whenever you get any of this data from the subsurface, it's always subject to interpretation and QC. So what is a poor geoscientist to do when you've got all these algorithms and you don't know? So what I will often do, since as you saw, this is running very quickly, I will extend what I just did. I will actually just basically just start from the beginning and just create each one, save them, put them all into a PowerPoint at the same scale, and then flip between them. Of course, I'll also look on the vertical displays of the seismic, and then I will decide which is my algorithm that works best with the type of data that I have. So does anybody have any questions or comments on that? Because as I say, these workstations, they give you so many scenarios, so many options. You need a strategy on how you're going to do it. And so again, what I do is when it's really quick, I just test them all. I build a file that's my reference file. That way, if in a final project presentation, someone says, why did you pick inverse distance to a power versus flex gridding? I've got it as backup. I can pull those slides and say why I did one versus the other. Any questions from anyone on that? Now, this was, by the way, the very quick summary. In fact, there's a lot more parameters you can control in here. And those of you who have worked with some of these algorithms know it. Of course, you can change your cell size. You can apply different smoothings of different kinds in here. And so that's the whole next level of detail once you've picked the first algorithm. And we're not going to go into all those. I just wanted you to see the principle of how when you have sparse data that we began with, a series of formation tops, in this case, you can grid that data.
I wanted to ask Mr. Allen.
Yeah.
So I do not really understand, like I understand that you will make every single one of them until you choose the one that is the best, but how do you know is the best? Like what condition should it involve, or I do not know that.
Yes, you see, so so it took me 3 minutes to teach you how to do this. It's going to take you 30 years to know how to pick the best. Now I'm I'm having some fun with you, but we're back to the thinking. We're back to the integration. So again, I was mostly trying to make you understand the principles of this. And as we say, each workstation will have 20 algorithms, one may have 100, one may have 5. Doesn't really matter what the algorithms are. But of course, what I would then do is come in and QC and see what this is telling me. So in some cases, you may only have well data. That's it. I mean, many basins, people don't work with 3D seismic. They're pursuing shallow prospects and they have no 3D, so they're using this. But bottom line is, you work with your data. And for example, what I would probably do next is come in and say, okay, so I've got a structure map. Now I want to see a cross section. I want to take an ARB line. I want to digitize an ARB line through some of these wells that I have the tops in. And then I'm going to want to look at my logs and see how this makes sense or doesn't make sense. So in this case, if we say cross-section depth, Let's see. Yeah. Zoom out. I'm going to play with the scale here in a moment. But now we get rid of the seismic, right? So in other words, now we're just in the depth domain. So we pretend we're now in the basin where there is no 3D seismic. So, of course, we were working on map D11, right? So we were working with the D11 top. Yeah, so let's take a look in here. Turn them all off. We'll turn these grids off. So basically what you can do then is like, here's natural neighbor. Okay, so of course what you're going to do is to compare how it looks with your tops and your logs, right? So that's the first kind of QC. So then let's see this next one. So you see, this is a case where the first one, it didn't interpolate as far, it stopped right there, you see. The gridding algorithm felt it didn't have enough confidence to extend the picking, so that was natural neighbor, whereas inverse distance, I actually went ahead and interpolated all the way through. And by the time you're finished, it may not necessarily match your formation tops 100%. You can see probably if I zoom in here, there's a little bit of error in here. So this is where you're going to use your judgment. Now, the next thing I would do actually is we saw how to flatten horizons. Well, of course, you can flatten grids. So grids, flatten, D11 inverse distance to a power. In this case, I want to see, I always like to see as much log above and below. So I'm just going to say 5,000 above, 5,000 below, flatten. And this is where, for example, I now start to see what did the algorithm do, and then how does it compare with my tops. So again, in this case, it doesn't match it perfectly here in well number 4, but maybe I judge that it's close enough. And of course, the next thing I will look at is the logs. I will look at how well the logs fit in there. So I know it's not a complete answer, but it's your other disciplines, it's your own knowledge and experience, and ultimately you see what you can accept. So if you can accept a little bit of error here, say at this particular well number 4, it may turn out you're very happy with inverse distance because it made you a map that covered a larger area. So I know this is just the beginning. I mean, Mr. Forrest may have a few points himself. He used to, you know, he was in the days where there were no gridding algorithms. The gridding was his hand. So tell us some of your thought processes as you were contouring, and you need to unmute yourself.
Okay, I just unmuted. Yeah, I grew up contouring by hand and doing all this stuff on paper. And it's, to me, it's a good learning way. It's a good education to go back and do that on your own sometimes. You know, that contouring by hand is kind of it's integration of the geology of the logs and the seismic. It makes you think about what the map should really look like. Sometimes these maps that we get out of the software are not really as good as a hand contoured map. So just, you got to be careful. You have to think your way through this all along. That's my point.
And this will ultimately bring you back to, you know, we talk about the regional geology and those stratigraphic columns, and that thinking should go into some of this. So again, if I were to look at, we said there was one map here that showed us an east-west trend versus a northeast-southwest. So if I know from my regional geology and some other work, for example, that I have deep mother salt features that are trending east-west, I might believe this one more than that one. So again, it's all about the multidisciplinary integration.
Everything's integration and thinking. You're right.
Exactly. So, you know, pushing the buttons is easy. Anyone can learn to push the buttons in the workstation. And like I said, so I taught you in 3 minutes the principles. You'll learn how to work with your 20 algorithms or 50 in Petrel in maybe a few days. But then it's the art of QCing and double checking all these different, and so back to the QC, it might turn out that in my ARB line, that top was incorrect. My grid was correct, but the top was incorrect. So you're back to having QC other things.
Alan, have you ever thought about wells, dry holes being drilled because of the lack of integration and thinking?
Oh, I think that happens all the time, and I think the most scary one is what our Egypt teams there showed today. To me, the worst is if you had something wrong in your projection system, and you did all this fantastic petrophysics and geology, and you just didn't load the data right in the first place. You send the rig, and it's 500 feet off. And that's too small of a distance for you to pick up when you were doing your projection QC, and yet that's going to be the difference between a producer and a dry hole. So, but I think that happens all the time. Geophysicists map something, and we talk about this all the time. Here's a bright spot. Okay, so if you don't integrate, you might go drill that. Whereas if you had talked to the geologist who had looked at the logs in this well, they would have told you this is a zone with no porosity. Don't go drilling. I mean, let's pick one even closer here. Let's go close to the well. Yeah, someone wants to come in and drill this bright spot right here. We'll pretend, and it looks beautiful on the amplitude map. Maybe it even shows AVO, but you didn't talk to the geologist who told you that this zone right here was a great big, we'll call it 100 millisecond limestone interval, and that all you had was interbedded limestone and shale. So that would be a geophysicist's dry hole, I would call that, because you did not
also have a strong amplitude anomaly at say geopressure, at the top of geopressures. If you have like in the offshore Texas Matagorda Island area, if you have a short change going into geopressures, that could be a very soft event. It's going to be a strong amplitude, and it's not hydrocarbons at all. It's just the top of geopressures.
Mm-hmm. But these are good questions because there's no simple answer to them. But usually, I think, as Mr. Forrest says, integration is the answer. Check with your reservoir engineer. What should be the pressure down at this depth? Maybe that is just a pressure boundary. It's not a real bright spot because of hydrocarbons. Or check with your geologist, or check with your petrophysicist. The integration is what is going to reduce the risk. So
it's all about back to the basics.
Yeah. So yeah, absolutely. So again, I mean, we all love fancy attributes, and we all love writing Python code that does this, that, and the other, but it's really the basics. 90% of your work is focusing on the basics and multidisciplinary collaboration. So I'm going to just mention, so we'll come back now to the time domain. And again, just wrap up on those grids. Just remember that a horizon, which you see on this menu here, is a very different animal, and I'm talking digitally speaking now, than a grid. So a grid like the one we just made, that you can export as a simple XYZ file. So for example, as long as the receiving person's project is in, of course, the exact same coordinate system as your own, you send a simple ASCII file that will not need a lot of cleanup. It's just going to be 3 columns. It should import very, very easily, and they should be able to duplicate your map directly with no errors in their workstation. Horizons are very different animals. Every workstation has its own format on how horizons are done. And horizons are tied to inline crossline space, if you want to think of it. And so, like I say, they're just very, very different animals. Don't confuse a horizon with a grid. So you have to know when you want to use horizons, when you want to use grids. Now, one feature I really like, and again, most workstations will have this to help bridge that gap, is a very nice little function called grid to horizon. So even though this was a grid that was not based on any seismic, so it's absolutely not a horizon, I use that function, grid to horizon, which then converts it to something that and let me see, the one natural neighbor, and then I'm going to call it D11 NN to save time, grid to horizon. Okay. So now what I've done, I have taken this grid. The program itself knows where that grid is, where the inlines and cross lines are. And it has now created that as a real horizon that the workstation understands. So I'm going to turn everything off other than the grid that has been converted to horizon. Oh, that's right. Yeah, I need to come back to depth to see it because it's still in depth. So cross-section depth should be there. It is in depth. And there it is. I see. Okay. So in this case, actually, it's got the negative numbers. So I think I'm going to have to convert that from subsea to regular depth. But anyway, the function grid to horizon, just be on the lookout for that because that is a very powerful function that lets you go across the two domains, the grids and horizons. Next thing I wanted to show quickly was just a couple of other steps to do with the QC. So again, I'm going to post data for where my wells with the tops are, wells, post data on map. And I'm going to pick any top, attribute map, formation tops. And I think all these wells, they all, if it had one top, they were all picked. But at least now I know where my wells are. So I'm going to pick another line, digitize arbitrary line, and let's just come across here, come through a few wells. We'll pull up the arb line. So now we are back, of course, in time. You can see the time scale. Now, because we have our time depth function, the wells are showing up because we have our check shots. Let's come back here to our horizon. So this one was in depth, but let's see if we can turn on a few horizons. And these were the ones you may recall we picked in our last session. C38. Okay, that's it. So anyway, so these are the tops. So I was just going to mention a couple of other functionalities. Again, there are different ways of displaying this in different systems, but this is one that I like, something which is called unit fill. And so what it does is you can see it takes the color of your horizon and it infills it. So this is very geological looking. And I often use this as sort of a QC. Now, what will happen is, as in this case, you may remember I picked and I auto-tracked over the entire 3D, but this also can be done as you go. And so in effect, you start with a blank section, and then as you click the horizon, it's color filling below. And so you can start again to think geologically, and you can put colors that fit the lithologies, and you can control that. And then this, there's things that you can control in addition, such as the transparency. So of course you control, I'm going to have to shrink this because it would usually be on the other screen. But I will often also use the transparency in here, or opacity to be exact. So if I want to think as a geologist, I might just hide the seismic in here. Or there are times when I may want to emphasize the seismic because I'm concentrating on the seismic, and I want to de-emphasize. Yeah, so it's almost transparent there. So let's pick something in between. And now hopefully, let's just say this is good. So now I see, the nice thing, as I said, you can use this on the fly. And so I see, for example, that I did not complete my picking here on the top of the green horizon. I'm going to go M for manual picking. There. And so I sometimes use this as I'm picking in real time because it makes it very obvious if I'm missing a piece of picking. Let's see, if I erase a piece here, I erase a piece there, I erase a piece there. So I would be seeing this and I would know that I need to come in and I've left a gap. So again, in this case, I'm not going to, well, let's try fill. 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 So this is more just think of it as a technique as a geophysicist that I use to make sure I haven't missed any piece of the interpretation that I wanted to see and things like that. So anyway, best practices I'm going to recommend, you can pick a certain number of inlines and cross lines. You use the tracker whenever you can, and you keep where the confidence is high. And then if you have some holes that you need to fill where your seismic data is not good enough, then you can use the grid in a small area to fill the holes. So now let's come back to, this is the amplitude map. Yeah. And again, remember we said it's always about playing with the color palette until it captures what you're thinking. And so, you know, this is another QC. I only put a few points in, as we saw earlier. I only picked 3 lines. I let the tracker work. So I'm also QCing, well, I QC the structure map to see if it makes sense. I'm also QCing the amplitudes to see if they make sense. And I'm going to say, if I saw like a straight line break in the amplitudes or something jumping up and down, like it jumps in vertical lines, it goes blue, green, in vertical lines, I know my tracker was having trouble. But me, first look here, that's actually not bad in terms of the amplitude display. It also pretty good in terms of the structure. But so in the real world, what you usually find happening is there's almost no area where your tracker will work 100% over the entire area, and yet you want your map to cover the whole area. So as I said, you use your tracker as far as it goes, and then you grid just to extrapolate into the holes. If you believe the horizon is present, by the way, you know, you're asking about these facies changes. Of course, if you believe the horizon has been truncated, your map needs to show the horizon terminating. So one other quick thing here. So, you know, we saw the unit fill. I'm going to show you something else I like to use, which brings us back to QC as well as interpretation. So see, once you get to the higher levels, you're kind of doing both at the same time. So, you know, here are gamma ray logs. And as we well know, you know, any log, especially if you've got, it's run by different operators, they may be good, they may be bad, there may be tool reading mistakes, or one petrophysicist use a different approach. So I also like to use this other technique here, which what it does is it uses, so this is integration. So we're still in time, by the way, on the seismic and the horizons. Of course, the wells are now converted to time. It uses the horizon picking that has been done by the geophysicist to extrapolate the logs. So we're just going to kind of illustrate that in here. So first thing, I need to make sure my various horizons are turned on in here. So here are my surfaces that I've picked, okay, that you've seen on the seismic. I'm going to use those. And now what I want to do is, in part, I want to QC the gamma ray. And it's thinking. So what has it done? It has interpolated my gamma ray log across my seismic, simply using the horizons I've picked as the guide. But this is an example of multidisciplinary work. In other words, you've got the person that did the picking, and they did that in the seismic. You've got in your case, you'll have your petrophysicist on the team who will have looked at the logs, may have done some edits. And then you bring them into the workstation, you look at them together. Now, as always, it's all about picking the right color palette. So in this case, that's not a very good default color palette. I would want to pick something that's closer. Let's RSA. I don't know if this one is a good one. Let's try. So the first thing is to get the palette, and then of course to play with the end member values. So it's re-interpolating my gamma rays. And I think I probably want, this is showing you only, I'm going to call it the thickest of sand. So let me just adjust the palette or the end member values. I don't know. Again, some of this is just trial and error. Let's just say, okay, apply. So again, the mechanics, 2 minutes. The thinking, the QC, etc. You know, you'll build that up. Okay, so there we go. So we're going to say, okay, so now I'm looking at the integration of the geophysical picking I have done with the logs. And so back to QC now. I look at this well, and I say, you know, when I look at the first 3 to the right, you know, it looks kind of geological. I can see what these probably these sands that are appearing continuous, and I can see some thickening and thinning. So maybe, you know, this looks kind of reasonable. But I come to well number 10 and suddenly look at how everything is turned up, so to speak. The volume is turned up. So as part of my QC, I would immediately go back to my petrophysicist and I would say, hey, can you please take a look at that well? And could you double check that it's been calibrated in the same way as the other wells around it? And actually looking at well number 6 here on the right may be a little bit off. So maybe one night he was working on well 10 and 6 and did the work one way, and then the other nights the petrophysicist was working on the other 3 and did not have internal consistency. So I, as a geophysicist now, am QCing my petrophysicist. And so I always say, yeah, show me the geophysics, the seismic interpretation. I love it, but that's just the beginning. It's not the end until you have done all the well work, including cores, all those things I just showed you a moment ago. Remarks, you know, maybe something happened, a drilling event that caused something. So it's all about the wells. Ultimately, your dry holes, your failures will be how well did you integrate your well information. And the wells are far, far harder to work, far more tedious, as we see, you know, as you saw in the cleanup of those logs, for example, or those ASCII files. That's the challenge. It's the wells, it's not the seismic. The seismic, once you get it in there, you know, unless, like I say, okay, you got bad data, you may have to reprocess, you may have to do a PSDM, which may take you a long time. But the wells are what's going to differentiate you. The wells are going to be the difference ultimately between success and failure.